When you move from the idea of containers into actually understanding how containerized software is delivered and reused, the center of gravity shifts to images. Images are the artifacts that travel between systems, the templates that let you reproduce an application environment, and the objects that make container behavior predictable across machines. The exam-level challenge is that images can sound like simple files, but they behave more like structured bundles with identities, versions, and internal history. The words you hear most often around images, pull, build, tag, and layers, are really describing different parts of that structure and how it changes over time. In this episode, we build a clear mental model of image operations and why they matter without turning it into a typing lesson. We also explore how Dockerfile directives shape images at a high level, because the directives are how an image's contents and behavior are defined. If you can explain what pulling does, what building does, why tags matter, and how layers affect reuse and troubleshooting, you will be able to reason through most Linux plus container image questions confidently. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Pulling an image is the act of retrieving it from a registry, which is a repository of images that systems can download from. Conceptually, pulling is like downloading a package template so your host can create containers from it. The important part is that an image is not just one blob, because images are commonly composed of layers, and the pull process often fetches those layers. If your system already has some of the layers from previous pulls, it might not need to download them again, which is why pulling can be fast after the first time. That layered reuse is one reason containers became popular, because common base layers can be shared across many images, reducing network transfer and storage duplication. Another key point is that pulling is tied to identity and trust. You are not only downloading content, you are accepting that the content corresponds to a particular image name and tag, and you are relying on the registry and related verification mechanisms to deliver what you asked for. At exam level, pulling is about acquiring the template from an external source, not about creating a new template yourself. Building an image is the process of creating a new image locally, usually from a recipe that defines what files and settings should be included. That recipe is often expressed in a Dockerfile, which contains directives that tell the build system what base image to start from and what steps to apply. The build process produces an image that can be run as containers on the local host, and it can also be pushed to a registry later for others to pull. A key beginner misconception is to think that building and running are the same thing, but building produces the template, while running produces the instance. Building also tends to emphasize repeatability, because the goal is to be able to produce the same image again in the future from the same recipe and inputs. If a build depends on external downloads, the image might change if those external sources change, which is why build determinism matters for security and reliability. At exam level, you should connect building to the idea of creating a custom image from instructions, rather than just using something pre-made. Tags are the human-friendly labels that help you refer to specific image versions, and they are crucial for keeping images organized. A tag is often used like a version name, such as a stable label, a major version label, or a specific release label. The trap is that a tag is not necessarily immutable, meaning the same tag name could point to different underlying content at different times if the registry updates what the tag refers to. This is why relying on a vague tag like latest can create surprises, because the content behind it might change without you noticing, leading to new behavior or new vulnerabilities when you pull again. A more predictable approach is to use specific tags that represent known versions, because that makes it easier to reason about what is running. Tags also matter for lifecycle management, because they allow multiple versions of an image to exist simultaneously and be referenced intentionally. For exam thinking, treat tags as pointers that help humans select an image version, but remember that the pointer can move unless you choose immutability mechanisms. Layers are one of the most important internal concepts because they explain both performance and many confusing image behaviors. An image is typically built as a stack of layers, where each layer represents a set of file system changes applied on top of what came before. A base image provides the lower layers, and then your build steps add additional layers on top. This layered model allows reuse, because if two images share the same base layers, those layers can be stored once and referenced by both images. It also affects build speed, because build systems can cache layers and reuse them when inputs have not changed. The subtle part for beginners is that each change step can create a new layer, and if you make a change early in the build sequence, it can invalidate cache for later layers. That means the order of build steps influences both performance and the predictability of what is included. At exam level, you do not need to optimize builds, but you do need to understand that images are built in steps, and those steps become layers. The layer concept also shapes storage behavior and what happens when you run containers. When a container runs, it usually uses the image layers as a read-only foundation and then adds a writable layer for changes made during runtime. That writable layer sits on top of the image stack, which allows the container to behave as if it has a mutable file system while still sharing the underlying image layers with other containers. This is efficient, but it also creates a key troubleshooting insight. Changes inside a running container do not modify the image itself. If you stop and remove the container, those changes vanish unless they were stored in persistent storage outside the container's writable layer. When you keep layers in mind, you can explain why a container seems to revert to an earlier state after recreation. The image layers are the stable foundation, and the writable layer is temporary. For exam scenarios that involve missing changes or unexpected resets, layer boundaries are often the explanation. Now we can turn to Dockerfile directive behavior at a high level, because directives define how layers are produced and what the container will do when it starts. A Dockerfile usually begins by specifying a base image, which establishes the starting layers and environment. Then it applies directives that add files, install dependencies, set environment variables, and declare what process should run by default. Each directive has a particular intent, and understanding intent is more important than memorizing every keyword. Some directives change the file system by adding or modifying content, while others change metadata, like default settings or startup behavior. The common pattern is that directives are processed in order, and each meaningful file system change tends to result in a new layer. This is why the Dockerfile is a recipe with a history. The order of directives defines the final result and influences caching. At exam level, the key idea is that Dockerfile directives shape both the contents of the image and the default behavior of containers created from it. One directive behavior that trips up beginners is the difference between building time actions and runtime behavior. When you build an image, you might perform steps that install software or prepare files, and those steps become part of the image. When you run a container, the default command and entry behavior determine what process starts. If you confuse build time and runtime, you might expect a build step to execute every time the container starts, or you might expect a runtime command to permanently modify the image. In reality, build time steps happen once when the image is produced, and runtime behavior happens each time a container is started from that image. This distinction is especially important for understanding reproducibility and troubleshooting. If a container behaves differently than expected at runtime, the cause could be in the image content, the declared startup behavior, or runtime overrides, but it is not that the build is still running. Keeping build and run separate in your mind helps you interpret questions about why a container starts and exits immediately, or why an application does not appear to be installed. The answer is often about where that behavior is defined. Another directive-related idea is that images carry metadata that influences runtime, such as environment settings and exposed ports. Beginners sometimes assume these settings automatically create network access or automatically secure a container, but they are better understood as declarations and defaults. If an image declares that a service listens on a particular port, that helps document intent and can guide container runtime configuration, but it does not guarantee the service is reachable from outside. If an image sets an environment variable that influences application behavior, but it can still be overridden at runtime. This matters because image definitions try to make containers portable, but portability still depends on the runtime environment and how the container is launched. At exam level, the point is that Dockerfile directives establish defaults and structure, but the runtime still controls how the container is integrated into the host's networking and storage. Confusing declarations with guarantees is a common beginner mistake. Tags and layers also connect to trust and rollback thinking, which is part of why Linux Plus includes these topics. If you rely on moving tags, you might pull a different image tomorrow than the one you tested today, which can introduce unexpected changes. If you keep track of specific tags and understand that images are composed of layers, you can reason about what changed when a new build is created. Layers can also support efficient distribution, but they can make it harder for beginners to grasp what is actually inside an image unless they think in terms of incremental file system changes. When something breaks after a rebuild, the question often becomes which layer introduced the change, which is another way of asking which build step changed behavior. Even without doing hands-on inspection, the mental model helps you understand that images are not just one file and that small changes can ripple through builds depending on directive order and caching. The exam rewards learners who can explain these relationships clearly because they demonstrate real understanding. By the end of this episode, you should be able to describe image operations as part of a coherent lifecycle. Pulling retrieves an image from a registry so you can run containers based on it, while building creates a new image locally from a recipe, often a Dockerfile. Tagging provides human-friendly labels that help you select image versions, but tags can be stable or moving, so predictable systems prefer explicit version tags. Layers are the internal structure that makes images efficient to distribute and cache, and they also explain why container changes do not modify the image. Dockerfile directives define what goes into the image and what the container will do by default when it starts, and they are processed in order, often producing layers that represent incremental changes. When you keep these concepts aligned, image behavior becomes explainable instead of magical, and you are ready to move into running containers and understanding how runtime settings like environment variables, logging, and inspection fit into the bigger picture.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.